Okay, so good morning, everyone. Thanks for joining in this session of today. And we are fortunate enough to have Indranil Roy. So a brief introduction of Indranil Da. So first he did his BSc bachelor's in St. Xavier's, Kolkata, and then he moved to TIFR, and he has been working with STM, the scanning tunneling microscope there in superconductivity lab, and now he's doing some wonderful studies in his Weizmann and Zeldov's lab. So we are going to hear from him today, and it's all over to you, Indranil.
Thank you for the introduction. I was actually thinking about introducing me for those who don't know me.
But... yeah, please do that.
Yeah, I mean, you have already said it. Anyway, so the work I'll be talking about is like recently. Okay, I'll also stop my video, otherwise this could be okay. All right, so the work I'll be talking about is done in Weizmann Institute, and it's recently published in Nature. Now, the work was mostly done by Amit Steinberg and Tobias Volkel here. Now, since this is a kind of a informal interaction, I'll be sort of not looking at the time limit. I'll probably go slower and explain.
Yeah, that's fine.
Slide by slide. Otherwise, this talk is sort of intended to be 25 minutes or like something like that, but I'll probably take a few minutes more. Anyway, so going back in the talk, let's start with something you can get something. I can't see the heading anyway. So before I start talking about the hydrodynamic flow, when we have a device, any device, any sample, and we measure, say, we send a current and we measure the voltage, what happens is what determines how the sample behaves is determined by a few length scales. And I'll talk about 3 length scales, which are very important in case of any transport measurement or even any realistic measurement in any device. The first length scale is it's called the momentum relaxing mean free path, and it comes because the electrons collide with impurities or phonons in the system, and this is a kind of external scattering in the device. The other kind of length scale is a momentum conserving mean free path, and that comes because the electrons also scatter between themselves, and it's an internal scattering. So the LMR, which is the external scattering, that sort of relaxes the momentum, but on the other hand, the electron-electron scattering that conserves the momentum. And the third length scale is the system size, which is so W. And depending on this 3 length scales, we can be either in one regime where, so the momentum relaxing mean free path is very small compared to the system size, as well as the internal scattering length scale. And that gives to a ohmic transport. That means you are sending some electrons in the device. The electrons are scattering from the impurities or the phonons, and you are measuring some voltage. Now, this kind of scenario, this kind of length scale problem can be dealt in the picture of the Drude theory. And on the other hand, if we have the other kind of a length scale problem where the system size is very small compared to the both the mean free path, then we have ballistic transport. That means the electrons, they scatter off the edges of the device, and one can actually explain this in terms of some billiard ball picture. Now, this is very common in very clean system, for example, graphene, the right-hand side, whereas the left-hand side is true for almost any metal. And in the middle, we have something where like the momentum conserving mean free path is very small compared to the system size. which is again very small compared to the external scattering length scale. And in this picture, we observe a viscous electron flow. That means if we are sending some amount of electron in the system, they flow like a fluid, like water flowing through a channel. And one can observe this in experiments, and this is called the hydrodynamic flow, and this is what I will be talking about. So the way to describe this hydrodynamic flow is for any fluid, in fact, is the Navier-Stokes equation. And the Navier-Stokes equation in its steady state and in an electrodynamics problem looks like this equation here, where eta is called the kinematic viscosity and is proportional to the momentum conserving mean free path. So this term is causes the momentum diffusion in the system. The second term is a momentum relaxation term, and this MR, tau MR, is actually related to the momentum relaxing mean free path. And we have a driving force, electric field in the system. And these three terms conspire to actually give the hydrodynamic flow in the system. Now, one can actually have a nonlinear term like this V dot gradient of V term in the equation. And in general, this type of nonlinear term gives rise to turbulent flow in system. For example, in any fluid, this fourth term actually gives vortices or any turbulence. But here, the thing is that the electron fluid has a very low Reynolds number, so we can actually forget about this fourth term. Now, one can ask this question that whether forgetting about this fourth term, this nonlinear term, can give rise to any hydrodynamic flow or not. The answer is that yes, it can, because we have a non-local relation between J and E, and that actually gives rise to the curl of J not being equal to zero, being non-zero. And that curl of J being non-zero actually gives rise to any vortices in the system. And there's a very famous paper by Grigory Falkovich and Leonid Levitov. And they showed in 2017 that even having this fourth term, this nonlinear term missing, one can have two types of flow in a device. The first being a simple laminar flow, where a current streamline flow from source to drain, these lines in the middle showed by this red rectangle. And the other could be the vertical flow, where current streamlines form closed loops. Now, this is very important because in turbulence, one doesn't talk about current streamlines. The streamlines don't exist, and actually the fluid mixes with itself. But here, without this nonlinear term, we see, one expect to see vertical flow where there are still current streamlines in the device, but they form closed loop. Now, one can express this Navier-Stokes equation in its linear form. One can rewrite it using two different parameters. The first parameter is called the Gurzhi length, where it's defined as a geometric mean between the momentum relaxing mean free path and momentum conserving mean free path. And of course, the conductivity, which is written in this general form. And the Navier-Stokes equation takes the form as written in the right. Now we'll be using this sort of rewritten Navier-Stokes equation for some simulation I'll be showing. Now,
so Indranil, sorry to interrupt. So
yeah,
can
sure.
I ask a quick question?
Yeah,
so,
sure. That would be great.
Yeah, so like just trying to understand how one can go from laminar to vertical flow. So let's say I am increasing the magnitude of current from source to drain. So will that drive a transition from, let's say, laminar flow to vertical flow just because the number of electrons are increasing? Yeah. Collisions are increasing, or like it is material specific, like what will be supported?
Yes, I think it's material specific, because the increasing the sort of, I mean, if we are taking the nonlinear term here, then yes, then if we are increasing the velocity, then what will increase is the chance of having turbulence. But for example, here what we have taken is the viscosity also has also a dependence on the velocity. So if we are increasing the electron flow velocity, so sort of like, then the kinematic viscosity increases, and that gives a more nonlinear relation. The nonlinear relation between J and E increases, and that also gives more chances to go from laminar to vertical flow. So yes, your answer, your question.
Okay,
Yes.
okay, fine, fine. And what is the meaning of this non-local relation between J and E? Means what exactly do you mean by the term non-local here?
Non-local, what I mean is, like, for example, you can you can write not in real space, in K space. So for example, you can write in J as a function of K is proportional or have some relation with E as a function of K. So that means that not only one, say, real space point value of J is determined by real space point of E, but you have to take the K space value in the wave vector. So it takes long range interaction.
Okay, fine.
Mm-hmm.
Okay, got it. Thanks. Yeah.
Okay. So, right. So now the question is like whether someone has observed this vertical flow in any system or not. And I'll be dividing the observations in two sections. One is transport, another is the imaging part. In transport, people have for a long time in graphene or gallium arsenide system, people have observed negative local resistance. And people have tried to explain this negative local resistance in terms of vertical flow. So this blue and red picture explains how a negative local resistance can occur because of vertical flow. On the other hand, for imaging, people have tried to observe Poiseuille flow through narrow channels. And there are some very nice work by Shah-Lilani's group in Weizmann, where they have used single electron transistor. Or there's work from Amir Yacobi's group in Harvard, where they have used in-center magnetometry to show that electrons can have Poiseuille flow in a narrow channel. And what recent work using this in-center magnetometry shows that in tungsten ditelluride, people have observed this Poiseuille flow, which is a signature of hydrodynamic flow. There's also scanning gate imaging, which is also done in gallium arsenide sample in 2018, which also talks about negative local resistance. Now, all this data, all this negative local resistance or Poiseuille flow data, this point to some hydrodynamic nature of electron fluid at some limit. And there's a very sort of interesting and informative article in Physics Today by Marco Pollini and Andre Geim, where they stated that we should be watching out for beautiful images of electron whirlpools because they'll be coming very soon. And it came out very soon in sort of when we observed the electron whirlpools in tungsten ditelluride. Now, I'll be talking about like tungsten ditelluride. That's our material of choice. And you got probably like many of you know tungsten ditelluride as a transition metal dichalcogenide, or a layered material, which in its monolayer form supports a quantum spin-Hall state, and it's a Weyl semimetal. But for us, we don't care about the transition metal. We care about layered material because we sort of use very thin flake of tungsten ditelluride. There is some question in the chat, or?
Yes. So the question is, what is the length scale of measured local resistance?
Okay, I'll just give me a minute. I'll
Yeah, fine.
Because in tungsten ditelluride I'll talk about that. Just give me a minute. Right. So we don't care about the quantum spin-Hall state. Okay. So we exfoliate our tungsten ditelluride single crystals into thin flakes of thickness of about 40 nanometer, and they have a very high charge carrier density because being a semi-metal, and that actually helps us in observing the hydrodynamic flow. Other than that, we don't have much use of these other properties of tungsten ditelluride. Tungsten ditelluride, on the other hand, has a very interesting property that its surface oxidizes very fast. But on the other hand, it's the surface oxidation is a self-limiting process, and it generally the oxidation stops within less than 5 nanometer thickness. On the other hand, we in Marcus Wicker's lab in Weizmann, they grow extraordinary quality of crystals, which have very high mobility bulk samples, having momentum. Yeah, so the LMR, the momentum relaxing mean free path, having a length scale of about 20 micron. So I think Shobik's question's answer could be this one, that for tungsten ditelluride in bulk, the length scale, the momentum relaxing length scale is about 20 micron. But for thin flakes, which have a thickness of about 40 nanometer, which we'll be using, has LMR of about 500 nanometer. All right, so the measurement setup which I'll be showing is called a scanning SQUID microscopy, scanning SQUID on tip, or SOT. And the way we make it is we pull a glass pipette to about 30 to 400 nanometer diameter apex. So this forms a needle kind of a a needle, and then we deposit lead to form 3 leads, 3 depositions, one on the one side, another on the other side, and then one on the apex. Now this 3 deposition forms 2 superconducting leads, and a SQUID loop is formed by these 2 weak links between the superconducting leads. And this is a scanning electron microscopy image of this SQUID-on-tip. These are lead films, and the diameter of the SQUID is about 130 nanometer here, this one. And we can actually go to a loop diameter of about 40 nanometer at the minimum, and the SQUID can operate up to about 1 Tesla. And our field resolution is limited to up to like 50 nanotesla per square root hertz. On the other hand, our spin noise is about 0.3 Bohr magneton per square root hertz. So using this, we can actually detect one single spin of one electron. Now,
sorry.
yeah.
Shobik is asking, is there any particular reason of choosing 50 nanometer thick WT2?
Sorry?
Shobik is asking, is there any particular reason for choosing the thickness as like 40 to 50 nanometer thick of WT2?
At first, no, but the thing is that for choosing 40 nanometer, no. So we sort of exfoliated and it turned out to be 40 or 50 nanometer, the flakes from the single crystal. And on top of that, we used lithography to pattern the geometry of our choice. So 40 to 50 nanometer was helpful in the sense that we wanted to go to as thin as possible, but less than that we didn't try, I think. But on the other hand, limiting it to 40 to 50 nanometer actually decreased the momentum relaxing mean free path, and that actually changed how the hydrodynamic flow happens in the system.
Okay, and there is a question from Joydeep whether like the evaporation or metal deposition is via sputtering or not. It seems very delicate.
No, this one is done by thermal evaporation, the regular thermal evaporation,
okay.
but not actually regular, because this superconducting thin film which we deposit on the glass, that doesn't stick to glass. So to make it stick to the glass, what we do is we cool down the this glass glass pipette using liquid helium to about 4 to 6 Kelvin, and then we deposit the material on top of it so that the film sticks and forms a superconducting lead.
Okay, yeah, that's amazing. Yeah, okay.
But we can also do it with using sputtering. Yes, we do it, but not lead, some other material. Okay, so to do now this is the scanning SQUID. Now to make it really scanning, what we do is we attach it to a tuning fork, and we use the tuning fork to bring the tip close on the surface of the device, and then we do our scanning. And we can scan up to a scanning height of about 50 nanometers. So this is like the tip and the tuning fork is hovering over the device over a 50 nanometer height. Now to give you how the measurement scheme looks like, we take a device which looks like this, a bar of some material, and then we bring our scanning SQUID on top of it, and we pass a current I0. Now, if we pass a current I0, then the current profile over this narrow channel, narrow or wide channel, doesn't matter for now, but this current profile over this channel looks like this. This is a simulation. This is the JY. So red means the current is going upwards. Blue means the current is going downwards. Now the current is going from bottom to top because of this current I0. So what we do is we raster our scanning SQUID on top of this channel. And what we measure is BZ, the magnetic field, as a function of X and Y. Magnetic field as in units of microtesla. So this red means the magnetic field is pointing out of the screen. blue means the magnetic field is pointing inside the screen. And one can actually reconstruct from this magnetic field data Jx and Jy, and the reconstruction from this Bz looks like the image at the right. So this is Jy, which matches exactly with the starting point, the simulated Jy for this kind of channel.
So you have to shield from the Earth's magnetic field for doing these measurements?
No, the thing is that the SQUID actually detects whatever the change of magnetic field there is. So if there's a DC background, the SQUID can actually detect whatever the change there is. So BZ is actually the change.
Nice. Yeah.
Because we also the thing is that the SQUID doesn't operate at zero field. So the SQUID operates at some specific magnetic field. So because of that, there is always a DC background. So we measured the the variation of over that DC background. Okay, so now we shift our interest to a geometry which looks like this one in the middle. There's a narrow channel, and the narrow channel is connected to two large chambers. Now we'll be flowing a current I0, and we start with measuring what's the effect of this current I0 in a regular metal geometry, metal device. It's made of gold. And this is the optical image of the gold device. Now, this gold device is defined by 3 parameters. Number 1, of course, is the width of this narrow channel. And the chambers are defined with the radius r and the opening angle theta. Now, for all the devices I'll be showing, the ratio between r and w will be the same. And w is about 550 nanometer. So the schematic of our device and our measurements looks like this. We pass a current of about 50 microampere, and there's a source. This is the drain, and we have a SOT which will be scanning over the gold device. And all the measurements are done at 4.5 Kelvin. Now, for an opening angle of about 180 degree, this theta being 180 degree, we measure the BZ, which looks like this. We can reconstruct the current density, and this is how the JY and JX looks like. So JY being red means the current is going upwards. JX, blue, means the current is going left. Red means the current is going right. So here the current, the streamline of the current looks like this. It's going up because of the JY, and red going right, blue going left, and then again going to drain. So one can actually use COMSOL to like a software called COMSOL to do ohmic simulations of this geometry. And the ohmic simulation using these parameters, that the momentum relaxing mean free path is much less than W, and we have the Ohm's law valid here, and then one gets for this geometry, the current streamlines look like this. On the other hand, if we go to a narrower opening angle of theta equal to 45 degree, then the BZ looks like this. And the current density reconstruction looks like JY and JX. But still, the current flows like a streamline in only one direction. It goes up, it makes a loop, but goes up. So it's still in a laminar flow. Although we have a chamber which with a very narrow opening. The current is still streamline. Well, the current is still laminar. Now we replace our gold with tungsten ditelluride, and we do the same kind of measurement. We start with a opening angle of 120 degree, and this is the BZ. The current density reconstruction gives a JX and JY profile like this. But here for 120 degree, the current is laminar, as is shown here, this one. We go to a theta of about 20 degree. And this is the BZ, how it looks like. The current density reconstruction for JY looks like this. It's always red in the channel, so the current is flowing upwards. But in the chamber, the JX has a difference. The difference being it's red at the opening, then it becomes blue, then red, then blue, and it flows back. So if we draw a streamline here, then it will look like this. So it flows from here to here and flows back. But in the chamber, it flows on the opposite side because red flows to the right, blue to the left. So this one is well, this can be checked whether this is correct or not using again simulations. And for the simulation, we have to take for hydrodynamic flow, if it's a hydrodynamic flow or not, that's what we want to check. And that's why we take the assumption that LMC, the momentum conserving mean free path, is much less than W, and which is much less than the momentum relaxing mean free path. And we use the linearized Navier-Stokes equation, and we use D to be of this form. And finite element COMSOL simulation gives a JY and JX profile like this for the same theta. And the streamlines looks like this. This is still laminar for 120 degree, but if we go to just 20 degree, then the COMSOL simulation looks like these two profiles, JX and JY, and the streamline flow looks like this. So we have laminar flow in the channel, but in the chamber, we have vortical flow. So the current is flowing on the other direction. So to do like, okay, I mean, in experiment, we cannot measure for continuous values of theta. That we can do in simulation, in COMSOL simulation. And in COMSOL simulation, to sort of have, parameterize the phase space of vertical to laminar transition, I'll be using a parameter, a quantity called IV over I naught, and that is defined in this integral form. Now, to give a picture representation of how this integral looks like, is that if we take a line cut of JY along the width of the chamber, then for laminar flow, the current profile JY over J naught looks like this green curve here. On the other hand, if we are in the vertical regime, then the current profile JY looks like this red curve here. And the integral does is it takes these two regions, the area under this red curve here, these two pink area, and what they represent is how much current is flowing on the opposite direction. And using this IV over I naught quantity, we'll be doing COMSOL simulation, and what this phase space shows is that for a certain value of d over w and opening angle theta, one can divide the phase space into two parts. One, the red one, where the IV over I naught is finite, and the other, it's 0. Finite meaning there is a vortex in the system. On the other hand, 0 means there's no vortex. So vortex to no vortex phase space looks like this. And one can have a sort of D equal to W line. And depending on that, one can divide the phase space into two parts. The one is that for very low theta, the vortex to no vortex phase boundary is, well, kind of linear. On the other hand, for large theta, the boundary does not almost depend on theta at all. Now, all this simulation is done using a no slip boundary condition. That means the current density at the boundary is 0 for the simulation. One can have a different kind of boundary condition, which is called a no stress boundary condition, where the divergence of J parallel at the boundary and the perpendicular component of that divergence is 0. So this is kind of a convoluted form of boundary condition, and that gives us a phase space which looks similar but has certain differences. The first difference being that the vortex state is much more stronger here at very high, well, not very high, at D greater than W region, and the vortex to no vortex phase boundary is much more linear in the no stress boundary condition. So what we will be doing is we will check how the boundary conditions actually matter for our device. And to do that, we have, in the left, our experimental data for theta equal to 20 degree. And we first do a simulation for no slip boundary condition, where slip length, which is defined as this in this equation, xi is called the slip length. The slip length is 0 for no slip boundary condition, and the Jx profile looks like this. On the other hand, one can have a no stress boundary condition where the slip length is infinite and the current profile looks like this. And in the middle, one can have a finite number of finite slip length of about, say, 200 nanometer, which gives Jx profile like this. On the other hand, we can take another example of about, say, 35 degree. This is experimental data on the left, and these three are the simulations. So if we compare the simulation with the experiment, we see that for experiment, this blue and red regions inside the chamber and in the channel, they are almost comparable, which is not the case for no slip boundary condition. So, but they are almost the case for no stress and having a finite slip length boundary condition. So what we understand from this is that we are in a no stress kind of boundary condition here. So we take the no stress boundary condition phase space, and we start to find out where we are in this phase space for our material. So what we do is, well, we take our device, we do a finite element simulation using these parameters, but there's one catch. That the catch is that if we have a very clean system, then one can have a specular boundary condition, which gives rise to streamlines, which looks like this. And these are kind of a ballistic kind of a behavior, where again we have a the reverse going current loop inside the chamber, which can give rise to the same kind of observation which we have observed. But the thing is that if we have to differentiate between the specular boundary condition with the one I have shown you, we have to have a the solution of Boltzmann kinetic equation in this particular geometry. Since that is very cumbersome to do, and it's like very uh, you know simulation wise it's just not it's very hard to do. What we do is we look back to experiments again, and what we do is first we determine that there are two limits depending on the ratio over the Gurzhi length d and the width of the channel w. If d over w is greater than 1, then we have a ballistic kind of a behavior with specular boundary condition. On the other hand, if d over w is less than 1, then we have a hydrodynamic regime with a no stress boundary condition. So the signature of hydrodynamic behavior would be to look for how the vortex to no vortex, the vertical to laminar transition happens. Because if it's in the hydrodynamic regime, then the vertical to laminar transition angle is almost linear here. On the other hand, if it's ballistic, then it does not depend on the angle. So if we look for the vertical to laminar transition angle, and we find out that the angle is first of all small, not like say over 100 degree, if it's like about 40 degree, 50 degree, something like that. And then if we can establish that the transition boundary is linear, then we can say that it's in the hydrodynamic regime. So for that, we do some simulation and we fix our d over w to 1.5. The simulation looks like this. What happens is we change the theta, the angle, and it slowly goes from laminar, vertical to laminar transition. The streamlines slowly enter the chambers. Let me play it once again. So these red lines, they are slowly entering the chambers and the vortices are disappearing at the boundary. On the other hand, if we go to a d over w, which is something like say 0.3, then the simulation looks like this, that the red lines are going inside the chamber, the vortices are vanishing, but before vanishing, before disappearing, they break into, so in each chamber, one single vortex break into two vortices. Look carefully. So this is one vortex. So before disappearing, there are two vortices, these two blue lines. So this is another signature that if we observe a two vortex state, that means we are in the hydrodynamic regime. And also we have to look for, again, what I already told you, that the vertical to laminar transition angle. So we take four different opening angles. So, and then we do experiment, we measure the BZ and find out JX and JY. For theta equal to 90 degree, this is laminar flow. this is ohmic simulation. For theta equal to 72 degree, we have laminar flow. For theta equal to 35 degree, we have vertical flow inside the chamber. For theta equal to 54 degree, so okay, before going to 54 degree, we put our data points: 90 degree, 35 degree, 20 degree. This is 72 degree, I think. This is 120 degree. So all of these data points on our phase space, and one can already see that from the fact that the vertical to laminar transition angle, this opening angle being small, being about 50 degree. So we can already assume that the transition is in the hydrodynamic regime, but the final nail in the coffin comes from the 54 degree measurement, which which shows the laminar flow like this. But in the chamber, there are two vortices. So from there, we can find out the exact opening angle theta, 54 degree, and we can put it here. So from there, we can find out that we have in the y axis, we are at this dotted line here. And since we know the value of W in our geometry, we can find out the Gurzhi length D to about 155 nanometer. Now, okay, let me just go slightly faster here. And, okay, so what we can do to prove that it's okay, already we have proven using two data points, two sort of arguments that this is a hydrodynamic flow, that first of all, the angle at which the vertical to laminar transition happens is low. And second, we observe a two vortex state in the chamber. So that already proves that we are in the hydrodynamic regime. We can, we can look for more signature. The other signature being that if we increase the temperature of the system, of the electrons, then the Gurzhi length changes. And the Gurzhi length actually decreases if we increase the temperature because the mean free path decreases. And if that changes, then what we can do is we can find out the boundary where the vertical to laminar transition occurs. And to do that, what we do, we measure with 35 degree opening angle. And what we change is we change the current we are sending in the chamber. So we start with 50 microamps, that's the data here, this one. Then we increase to 100, 200, 300, and 400 microampere. And the 400 microampere shows here, this one, two vortex state, which is this point here. And sort of calculation, electronic calculation shows that 400 microamps correspond to about 18 Kelvin electronic temperature in the system. So by going from 4.5 Kelvin to 18 Kelvin, one can shift the phase boundary from here to here. So that the 35 degree angle phase boundary for higher temperature is this point. And we have actually now two data points, one at 4.5 Kelvin, this one, and another at 18 Kelvin, this one. And they more or less fit with a linear behavior. The vertical to laminar transition is kind of linear. So from these three signatures, one is the direct observation of the vortices. Two, the angle at which the transition occurs. 3, the 2 vortex state, and 4, the linear behavior of vortex to laminar transition, we can finally say that we directly observe electron vortices in tungsten ditelluride, and we are in a hydrodynamic regime. Now, before I finish, there's one small thing which I should mention, that the values of Gurzhi length which we get from this experiment, this fitting with this phase diagram, was about how much? It's like about 150 nanometer, and from there we can calculate the momentum relaxing and momentum conserving mean free path, because one of them we get directly from transport. The momentum relaxing mean free path we get from bulk transport to about 20 micron, and from there we get our momentum conserving mean free path to be very small. Now there is a discrepancy here, and discrepancy we solve the discrepancy by first realizing that in bulk system, although the momentum relaxing free path, which I have already told you, is about 20 micron, in thin flex, this momentum relaxing mean free path comes down to about 400 micron. But on the other hand, what we find out from some calculation, from theoretical calculation, that the momentum diffusion in our system does not occur from electron-electron interaction, but occurs from the electrons sort of reflecting from the surfaces of the crystal, and this reflection of electrons from the surface of the crystal actually gives rise to this hydrodynamic behavior. So we don't call it really hydrodynamic, we call it a para-hydrodynamic regime. Nonetheless, let me finish here by thanking the people who are actually involved in the further experiments now. So Tobias and Amit, they are now doing similar kind of experiments in gallium arsenide samples. The sample was prepared by Arkady and Arnab, who are in Marcus Wicker's lab. Now Arnab has joined IISc as I think Inspire faculty. The theoretical simulation was done by Tobias, and this electron-electron interaction calculation, the theoretical calculation, was done by Levitov and Grigori Kalkufich. Okay, with that, let me thank you guys for listening to me, and you can ask questions if you want.
Yeah, thank you, Indranil, for the nice talk, and yeah, and it's actually a very elaborate work, and thanks for mentioning to us. And yeah, the floor is open to question. If someone has any question, can just unmute and ask. Okay, there might not be much question. Let me do one thing. I am stopping the recording now, and then we can discuss anything. Like if anyone has some outside academic question as well, like how the city life is there as well.